Hey students, we're going to talk about gears, pulley drives, and sprockets. So, just a quick overview. Why do we have gears, pulleys, and sprockets? Okay, these are what's called powertrain elements, and you see those quite a bit in all over the place. But typically, what you're most familiar with is if you've ever worked on a car, it is part of transferring the power from the engines or engine to the wheels, okay, to make the car go. And we use these gears, pulleys, and sprockets in three different ways. We either want to change the speed of rotation, right? We start out in first gear and we have more torque to get the car going. Then as we accelerate, it changes into higher and higher gears that basically says, hey, you know what? If we start off with one turn of the engine equals one turn of the wheels, all right, then as we proceed down the road and we get faster and faster, we don't need that much torque. All right, we want to go faster. All right, so we might start saying, okay, one turn of the engine is two turns of the wheels, or one turn of the engine is now four turns of the wheels. When we reach interstate speeds. Okay, so we can change the speed of rotation. We can change the direction of rotation. So we can, when you put it into reverse, you are altering the gears such that the engine is driving in one direction, and then the gears that you've changed it into, the reverse gear, drives it in the other direction. Okay, and then what I just described, the last one, is just change the amount of torque available to do work. So pause the video, write this down. Okay, torque is the amount of power, in this case rotational power, that's available to do the work that we need to do. In case getting the car going, right? It's going to take more torque to start a car moving than it is to keep a car moving on the interstate at a at a flat level piece of ground. All right, gears. Okay, so gears and when we have multiple gears together, we call that a gear train. All right, it's a mechanism used for transmitting rotary motion and torque through interlocking teeth. And you can see the picture down here. There are teeth that lock together, all right, and then if this turns, the other one has to go with it. All right, so the gear train is two or more gears that are meshed. If they don't touch and they turn freely, they are not a gear train. And then we have the driver gear. All right, so if you think about, if you're in the car, if you're the driver, you are the one controlling all of the motion. All right, and then you have the driven gear. Okay, so driver gear is the one controlling all the motion. Driven gear is the one that goes along for the ride. Okay, so the driver one is turning. All right, the driven, all right, if you're in the car and you're the passenger, you're being driven around. The driven one is just along for the ride. Okay, so the driver is in control. Okay, and so here's an example of them being meshed together. Okay, so they fit together. They have the teeth that lock together, and you can see that in the picture there. They always turn in opposite directions. So if you look at the blue one, it turns in one direction. It's turning like this, and then the red turns in the opposite direction. All right. Occasionally, right, you want them to turn together. And so you might put an idler gear right here, idler gear, that allows the driver and the driven to rotate in the same direction. So we have an idler gear here. Okay, this one turns clockwise, and if we say this is the driver, this is the one that has power, right? This is the idler, and this one is also turning in the same direction, but it's the driven because power is coming off of this shaft. Okay. And it may seem weird to say, but you want the teeth to be the same size. You don't want to try to mate, something with very large teeth with something that has very widely spaced teeth. The teeth need to be the same size for this interlocking. Okay. The RPM, so rotations per minute of the larger gear, is always slower than the rotations per minute of the smaller gear. Okay. Think about this. Okay. There's a certain amount of gear teeth that can fit around the outside. If you have more teeth, it's going to take you longer to rotate around than if it's something that has smaller teeth. So if it's a bigger gear, it's always turning slower than a smaller gear. Okay, if they have the same size teeth. If the gears are locked together, okay, so if we look at this yellow one, right, it's going to be turning slower than this red one, right, because it's the bigger gear. If it is locked on the same axle, so this axle runs all the way through, and this gear are on the same axle, they turn together regardless of size, okay, because they're locked together. They're both being driven at the same rate, okay. So when you look at this slide, it is very easy to just go, wow, Mr. D, that is a lot of just stuff, and I don't care. I just want to. It's really simple. Okay, you do need to write this down because we're going to talk about it for the next 5-6 minutes or so. Okay, so variables to know. Okay, N is going to be the number of teeth. All right, and we're going to use each of these to calculate how much torque, what our gear ratio is. Okay, so I can have number of teeth. All right, and I can count here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right, this has 12 teeth. This one has 1, 2, 3, 4, 5, 6. This one has 6 teeth. All right, D is equal to diameter, how wide it is. All right, this one is wider than this one. Right? We have this W, and this is not actually W. This is the lowercase Greek letter omega. Okay, it's easier if you just think about drawing a W, but that's angular velocity, or the easiest way to think about that is the speed at which the gear is turning. Okay, if we want to be super correct, right, it's how fast, it's the rate of change for you pick a tooth, how fast is that angle between it and the center changing. Okay, but just think about it, it's the speed of the gear. Turning slow, low angular velocity. Turning really fast, high angular velocity, right? Speed. And then we have this little T, okay, and that's for torque, and it makes it super easy to remember, but that's the lowercase tau, right? Another Greek alphabet. And you see that a lot in engineering. We assign a Greek letter to a concept. All right, so omega is angular velocity, lowercase t, tau, lowercase tau is torque. Okay, and that's relatively easy to remember. All right, and then we use subscripts. All right, so this is where it's written below. Subscripts in and out are used to distinguish between the gears. So number of teeth going in, number of teeth going out. Diameter going in, diameter going out. Angular velocity, how fast is it turning going in? 40 revolutions per minute. What's the velocity speed going out? 20 revolutions per minute. And then we have torque, we have 40 foot-pounds, and going out is 80 foot-pounds. Okay. So, equations that we need to know, all right, and we need to write this down, all right. GR, if you see me write, like, what's the GR? I'm meaning gear ratio. Okay. So we can think of gear ratio, and one thing so I put this over 1 because for some people it makes sense. If you want to think about that's not there at all, and just say gear ratio is equal to each of these things, that's fine. But some people wrap their head around it more mathematically. I can always divide anything by 1 without any consequences, because anything divided by 1 is itself. So I'm not changing it, right? So I can think of this as GR over 1, all right, or just GR. And if I know the number of teeth and if I have gears in front of me, I can count them. Number of teeth out versus number of teeth in. Okay. And we know, right, this is what's going in, right? This is the driven gear, right? The driven gear is the in. What comes out. Sorry, this is the driver. This is the driven, right? This is the one controlling. This is the one that's along for the ride. In is the driver. Out is driven. Okay, it's the passenger. So number out divided by number in. Number of teeth. Diameter 4. Out versus diameter in 2. All right, or angular velocity in divided by angular velocity out. Notice that's changed. All right, so we're going to be 40 divided by 20 there. All right, or torque out 20 divided by torque in. I'm sorry, that's not torque. Torque's not labeled on that picture, but we had 80 over 40. Okay, in each of these, right, we have, if we count those, there's 12 teeth there, 6 teeth there. All right, 12 over 6. On this case, distance 4, 2. Okay, 4, 2. 40, 20, and then one from before, 80 and 40. We can know from our problems or the reading of the problem that we set up, looking at our picture here, that in each of these cases, right, 12 divided by 6, 4 divided by 2, all right, we get a gear ratio of 2. Okay, and it's going to be a gear ratio of 2 to 1. All right, and that's why it's helpful to put that 1 underneath, all right, because it helps you that, okay, the gear ratio is 2 to 1. Right, so in this case, this needs to turn twice for this to turn once. Right, please, 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 please remember that gear ratios, just like mechanical advantage, are unitless. Okay, unitless, do not have a units. Inches divided by inches, cancel. Revolutions per minute over revolutions per minute, cancel. Foot-pounds over foot-pounds, cancel. Those units cancel, so you're left unitless. It's not 2 inches, it's not 2 RPM, it's not 2 foot-pounds, it's just 2 to 1. Right, 2. Okay, so if we look at the gear ratio between gears A and B, so we're looking at gear ratio A to B. Okay, so usually if we're saying observe it between the two, this is going to be your in, this is going to be your out. So A is going in, B is going out. So we count the number of teeth. Okay, I've got 20 in the first one, so 20 in, and I've got 12 out. So 12 divided by 20, 0.6. All right, or 0.6 to 1. All right, this is less than 1, so I know that I'm trading speed for torque. I'm trading, yeah, I'm gaining speed, I'm losing torque. That's what I mean by that, right? So this is going to turn 0.6 of the way for every turn of this one. Okay, so if we look at gear ratio between B and C, again, we just pull the data out. I've got 12 teeth here, I got 5 teeth here. Number out, divided by number in, 5 divided by 12, right? First letter is the in, okay, 0.42 to 1. And the same thing for the last one between C and D. Number out divided by number in. Number out's 20 divided by 5, 4 to 1. All right. So each of these gear ratios is changing as we go through here. Okay. But there's a trick, because that was a lot to get to. We had to do like 4 things of math to get to that. Okay. Here's the trick that will make your life simpler. You can do this if I ask you, all right, what's the total gear ratio, right? You could use this to figure that out. Or you could remember, oh, Mr. D, right? Idler gears, the ones in the middle, don't impact gear ratio. Okay? Because basically, this is going to turn at a rate, all right? And it doesn't matter what these do, okay? It's going to turn in the same ratio between this one and this one, okay? They're just locked together, all right? If you don't believe me, right, if I take what's the total gear ratio, okay, 0.6, 0.42, 4, right, and to calculate gear ratio, you just multiply them together. If I do that, I get 1 to 1, right? If I just said, okay, I'm looking at A and I'm looking at D, all right, number out divided by number in is 20, number out is 20, 20 divided by 20, it's 1, right? So regardless whether I calculate this individually, gear ratio between these two, gear ratio between these two, gear ratio between these two, right? That's why I've got 3, right? Equals 1. Or if I just say, okay, what's the gear ratio between A and D? Comes out to be the same thing, okay? So don't worry about the idler gears, except for direction, okay? Because this is going to turn, this one will turn opposite to this one, this one will turn opposite to this one, this one will turn opposite to this one, okay? Then if the last gear had 40 teeth, okay, what would be the gear ratio of this? You don't need to calculate everything, right? Number out divided by number in. Number out's 40, number in's 20. 40 divided by 20 simplifies to 2 over 1. Boom. All right, 2 to 1. Okay, and the first one here, right, is showing you that, you know, doing it where you calculate each one all the way, and it just shows that this whole idler gear doesn't work. You don't have to include those. Just proves that it's right. Okay. So kind of skipped ahead. I probably should have had this slide earlier, but if you're going to do gear ratio total, you're going to multiply them together. It's exactly the same as mechanical advantage. Mechanical advantage, we did those together. Okay. However, the point of this slide, okay, it looks like the same equation. It is not the same thing. All right, you're doing the same thing mathematically, but force and torque, not the same thing. All right, write that in your engineering notebook. All right, draw a little box around it. Force, torque, not equal, not the same thing. Okay, force is measured through a cable or a string. Okay, so I got a cable and I'm pulling or pushing on something. You can't really push a string, right? But think of a rod. Okay, force is measured through a cable or a rod. Okay, because I am pushing or pulling on that string. Okay, torque is measured about an axis of rotation. I have a point, I have the center that I am rotating about. Okay, the force and torque, not the same thing. Okay, that's the important part there. Okay, so all right, we use them similarly. Okay, for gear ratios, they only apply to torque. Mechanical advantage only applies to force. Okay, it's still products for both of them. You're going to take the mechanical advantage and add it up. Gear ratio, multiply it up. Gear ratio, multiply them up. Okay, but mechanical advantage is only used to calculate forces. Gear ratio is only used to calculate torques. I'll write that somewhere, maybe highlight it. Okay, super important. Okay, because I'm going to give you a machine that looks like this and be like, what's the gear ratio? Okay, and you're going to be completely confused. Okay, because this machine has a gear ratio and it has a mechanical advantage. Okay, this is really a compound machine in that there are a wheel and axle. All right, I've got a wheel and axle here. Here's my wheel. All right, wheel and axle from here. Wheel and axle for this. All right, and then in the middle, right, there's a gear train between the pink and the blue. Okay, so if we look at the wheel and axle, all right, we have to use a mechanical advantage because we're dealing with forces. All right, so mechanical advantage is the effort distance divided by the resistance distance. So we can pull that out of the information and know that our mechanical advantage is 2.67. All right, if we look at the gear train, we have to switch from mechanical advantage. Right, here we use mechanical advantage. All right, when we're looking at the gear train, we have to be cognizant. We have to use our brains in that, oh, okay, I'm doing a gear train, so now I got to switch to gear ratio. So number out divided by number in. I can count those. 24 divided by 60, and that's 0.4. And then for the last one, the last wheel and axle here, we got to use mechanical advantage. Effort distance divided by resistance distance. 0.6 divided by 4 inches. All right, and that gives us a mechanical advantage of 0.15. And then so we have two mechanical advantage there. We need to multiply them together to get the mechanical advantage total. All right, so 2.67 times the 0.15 equals 0.4 mechanical advantage. All right, and then our gear ratio, right, is just the gear ratio of the other. It also does not have to be the same. It could be something different. But in this case, it does come out to be the same. Gear ratio is also 0.4. And that's probably by design. Okay, that's a lot. Okay, just remember, okay, that gear ratio, mechanical advantage, one uses angular velocity, the other uses force. Not the same thing. Okay, so you got to keep those two separate. That's really, I mean, honestly, everything else we're doing is division. That's really just the hardest thing. Okay, so you got it now. You should be great. Okay, I don't know what they're doing with this slide. We're going to go to the next one. They're basically saying it's pretty common to do a compound gear because it allows you can change your torque up. All a compound gear is I have one axle with two gears on it, and as we said before, those two gears turn at the same speed. So in this case, these two, B and C, are going to have the angular velocity of the same speed because they're on the same axle. Okay, A is connected to B, all right, and C is connected to D in this case. All right, so the gear teeth mesh between C and D, and the gear teeth mesh between A and B. Okay, so if we look at just the gear ratio between A and B, we can calculate that out. Number out divided by number in. All right, so we're starting here. That's the first one I say. Number out is the second one, 40. Right, because these are the two they're touching. 40 divided by 10, that's going to give me a gear ratio of 4 to 1. All right, if I do the gear ratio between C and D, so here's C and D. It's hard to see with the red. All right, so it's 50 divided by 20. Again, simple math. You just have to put it together. All right, 2.5 to 1. Okay, if I want to get total gear ratio of the entire gear train of this compound gear, then I would multiply the two together. So I got 4 here, 4 to 1. I got 2.5 to 1. 4 times 2.5 equals 10. All right, 1 times 1 equals 1. All right, so I get a total gear ratio of 10 to 1. Okay, so in this case, it's above 1. I'm gaining mechanical advantage, so that means this needs to turn 10 times. All right, for D to turn 1 time, which means I am losing a lot of speed because this turns 10 for every single turn of this, but I'm gaining a lot of torque. This is going to have a lot of ability to apply a lot of power, okay, because I'm trading, instead of high speed, I'm going for high torque. Okay, and belts and pulleys, kind of the same way. The only real big difference, all right, is that they turn in the same direction. Okay, so here's your equations. They're just like before. D out divided by D in, or angular velocity in divided by angular velocity out, or torque out divided by torque in. Okay, notice that torque does, angular velocity does change up there, just like before. Okay. Remember, the units cancel. Okay. The key is that the direction is the same. Where you have gears, they operate opposite directions. Here, the pulleys both turn in the same direction. Okay. And then Same thing with sprocket and teeth, or sprocket and chain. Okay, it's really kind of the same thing as a pulley. They both rotate in the same direction. They still get the same equations. Okay, the only real difference, all right, is, and remember that the units cancel, the only difference is sprockets and gears are often confused. Okay, gears are going to mess directly, all right, while sprockets are really pulleys that have a chain instead of a belt. Okay, so you're using the chain to transfer power. In gears, you're using the teeth to transfer the power. All right, and this is probably my favorite slide. Not only is it the last slide, but it kind of is like, I don't understand. Like, you just threw, like, in the last two slides, you talked about gear for like 20 slides. But then like the last two slides, you did pulleys and sprockets. Okay, they're all treated the same except for pulleys and sprockets. The driven and the driver. So the driver is the one controlling, the one that's applying the motion. The driver, all right, and the driven are going in the same direction with the pulleys and the sprockets. Okay, well, Mr. D, what's the difference between a pulley and a sprocket? Okay, pulleys have a belt. It's usually fiber reinforced rubber. Okay, sprockets have a chain, just like on your bicycle. Okay, pulleys tend to be quieter. They usually don't require lubrication, or it's built into the belt, and they're cheap. You can buy a belt for your lawnmower for like $7-8. Okay. If we do a chain and a sprocket, they don't slip, which is very positive. All right, that's why we a lot of times have engine timing chains, because we don't want the timing to slip. And they're stronger, and they tend to last longer. Okay, which is why we see a lot of engine timing chains. Okay, the pulley's disadvantage is it can slip. All right, if you apply too much torque on one end or the other, your belt can slide. Okay, it can slip. It's just a friction fit. Sprockets can't do that, but because it's metal, it costs more. Both to the physical for the chain, the cost of the chain is much more expensive. Like, it might be a couple $100 or $100. Or if it's your bicycle, it's much more common, but it still costs more than a pulley. Usually about like double. It needs lubrication, and you spray it on your bike chain, especially when the timing chain in cars. They bury it in the motor, and they use the oil from the motor to lubricate it. And they tend to be noisier. So the chains, as it rattles over, you tend to hear it. You hear that noise, where pulleys can be much more silent. All right. Hope you enjoyed, and let's continue on with our lessons.